So the wide triangle, there, we can't get that one to go all the way down. It's just a little bit too thin for all the screws.
Oh,
So we also have the equilateral there that does go all the way
use
down.
that then.
Okay.
I'm going to need, I know this might work. Yeah, this will work.
Okay.
Change the date.
Oh, perfect. Thank you.
Are we live?
Yep.
Good morning, everyone. Welcome to another week of class. So I'd like to kind of start off where we left off on Friday with a discussion of total internal reflection. And if I could get Colton, one of you, maybe you to man the lights. Yep. I've got a light source here going into a piece of plastic. Let's go ahead and turn the lights on so people can get a look at that. I don't think we need to close the doors.
It's better for the camera.
It is? Okay. Okay, so you can see that we've got a piece of plastic here, and we've got a beam of light coming from this light source into it. And let's go ahead and turn the lights off then. And so we have the ray coming in here. We can see we've got a reflected ray coming off the same angle, going kind of up towards the ceiling. We have the light bending as it goes into the material, again from refraction, hitting the far side here, and some of the light escaping, but also we get another reflection right here, bouncing back down. You can even see the light kind of escaping down here below. If I change the angle though, you can see that as the angle gets shallower and shallower where it hits this surface on the backside, the ray that's refracted out of the material gets closer and closer to the surface, and then when it reaches the surface, we have the total internal reflection. So right now at this angle, all of the light is reflected inside the plastic, and none of it escapes the far side over here on the right. And something else that's kind of cool to note is if it escapes barely at a large angle, it's not your imagination. You can see kind of a rainbow here. Does everybody see that okay on the wood? That's because different colors of light are bent by different amounts. So this is here. You can see that the blue colors, the shorter wavelengths, are refracted more than the red colors, the longer wavelengths. But here we got the total internal reflection. Okay, lights please. And this is why fiber optics are so useful, in that we can send a signal of light into basically a filament of glass or plastic and have that light stay inside that filament or that fiber. And instead of sending our signals in terms of electrical signals inside conductors, usually copper is what's been typically used, we've now switched almost entirely to sending the same sort of information, but using little pulses of light. And the advantage of that is we can send a whole lot more signals through a teeny little fiber than we could through copper cables. In fact, it would take a stranded copper cable thicker than my arm to send the same amount of information that we can now through a single fiber optic fiber that's thinner than even one of your hairs. And that could be made of something very, very cheap like plastic or glass. And yet copper is very, very expensive. When I was a child, all of our long distance phone calls, for example, were carried by copper cables. Cables crisscrossing the United States with the cable bundles being thicker than my entire body. And that's a lot of metal, and it was a lot of expensive, very, very expensive. To the point where you had to pay, it was close to $1 per minute if you wanted to talk to a relative, say on the East Coast. It would not be unusual to, if you have a nice long conversation with somebody on a holiday, like a Thanksgiving or Christmas that's across the country, to see a bill for that single phone call to exceed $100. That was not that uncommon. It was very, very expensive to talk to people long distance, is the term that was used. And now we don't even keep track of it. It's like call anywhere in the United States or even the world, and it's about the same rate, depending on the network. And communication is incredibly cheap because of the use of fiber optic cables. So we could also use, actually, let me go back. This dispersion effect that we saw, where the light was split up into colors, we see that. Basically, focusing light is kind of like herding cats, in that the amount that light bends depends on the color. This is called dispersion. As you saw, red light is bent less when it goes from one material to another, and blue light is bent more. And that's why the old cameras were very, very expensive, because you could get a lens that could work really, really well to focus one color of light, but say if it was optimally designed for the red, anything blue would be kind of fuzzy. And then if you're trying to focus light on a photographic film, which is how the old cameras worked, well, you would have to use a combination of lenses to kind of balance things out and come up with a compromise so that all the colors would be focused close to the same. And this was, quite difficult. And even so, the images were not as crisp as, you would probably like them to be, because it was, again, kind of an optical compromise. And now we don't have that problem. Our cameras, but basically that's why the old cameras were very, very expensive. The lens combinations were very complex, sometimes involving a dozen lens elements or more. And now we have very, very simple cameras in comparison as far as the lens arrangement. There's just a single lens, but behind it, instead of photographic film, we have a charged couple device that basically receives the data and then creates an image based on what energy of, what color of light was incident at what part on the detector. And so it's not quite an eyeball, but it's pretty close. And we've got a software package that then adjusts for this chromatic aberration in the lens and creates an image that's sharp on all colors. And as we've had better and better cameras for your phones, what's not changed is how good the lenses are. It's the software that analyzes the information that is collected by the charged couple device, basically the optical sensor. That's what's made this picture so much higher resolution and so much better quality. It's not any sort of advances in the lenses, it's advances in the software for processing that information that you get on the charged couple device. But anyway, this dispersion is also why we see rainbows. And what's going on in a rainbow, I mentioned this briefly when we had the glass marbles out with the flashlights last week. and the light will come into a raindrop. It'll refract. It'll go into that raindrop and bend. And when the light refracts, well, the blue light is bent more and the red light is bent less. And then that light will bounce off of the backside of the raindrop and then come back out close to the front of the raindrop, bending again as the light goes back into air. Again, you're going to have the red light bend less and the blue light bend more. So this is kind of a cheesy little diagram of what's going on. In that, see, I got the sun over there. Light from the sun is represented by this white dowel coming in to the raindrop. And really, where it's entering the raindrop is not where I've shown where it's shown. In order for it to get to rainbow, the light has to enter in close to one edge. So, Brandon, the next time you do this, have the ray coming in closer in out here.
Okay.
And then it bounces off the back side and then comes out the front. And so these two rays ought to be down here. So the angles is right, but that needs to be shifted down. These need to be shifted down for it to be really, truly accurate. But anyway, with regards to the angles, at least, it looks pretty good. You got light from the sun coming into a raindrop, and what comes out is that white light is split up into different angles. The red light over here and the blue light down here. And so for this one raindrop, if you're down over by Braden's feet, you're going to see the raindrop look blue because that's where the blue light's coming. And if you're down over where Braden's waist is, that raindrop, the same raindrop, is going to look red because that's where the red light is going. And so when you look into the sky and you see different colored raindrops, the color of the raindrop you see is because you've got a very precise angle between you, that raindrop, and the sun. For a little bit of a smaller angle, you've got red raindrops, and a bit larger angle, you've got blue raindrops. And where you're going to have that same angle between you, the sun, saying that the sun really doesn't change position, but you can have lots of other different raindrops. You'll trace this out, and it will form an arc, basically a circle. Wherever you've got that same angle between you, the raindrop, and the sun is going to lie on a circle. But since we usually just see raindrops in the sky, we're only going to see a part of that arc. So that's why we see a rainbow. There are places where you can see more of a rainbow. Good example are waterfalls. When you stand above a waterfall in just the right position, sometimes you can see more of an arc. There's a prominence that sticks out over Shoshone Falls, for example. Shoshone Falls, that's over there in eastern Washington. There's a prominence that you can hike up to that's actually kind of famous to stand on there, and you can see about 2/3 of a rainbow at just the right time of the day when the sun's behind you. So if the sun's behind you and you're looking down into the mist of around the waterfall, because you're essentially you can be looking down onto a bunch of mist, you can see you can't see a full circle, but on a good day, you can see 2/3 of a circle. And if you've ever been in an airplane, if you look at the shadow of the plane on clouds below you, if the light is just right, you'll be able to see the full circle of the rainbow with the shadow of the cloud of the plane in the exact center of that rainbow. So that's another really cool optical phenomena. You had a question?
So why do you get double rainbows then?
When you get a double reflection. If you have light coming in at an even steeper angle, instead of just getting one reflection off the back, and then light coming out, you'll get a reflection, then another reflection, and then coming back out.
Huh.
And if you actually work out the geometry, that'll switch the order of the colors. So if you look at a rainbow and it's bright enough that you see it's not as likely to have that second reflection, so it's going to be less bright. But if it's really, really bright and there's a lot of raindrops, you might be able to see a double rainbow. There's been a couple of times in my life when I've actually seen a triple rainbow, but it's only been like 2 or 3 times in my life, and it's never been a full rainbow, it's only been a partial.
And the third rainbow is always super dim.
Yeah, and the second one is usually a lot dimmer than the first. In fact, barely perceptible. Something else to note is that if you see two rainbows, a double rainbow, the sky between the rainbows will look very, very dark. That's because the light that's coming into those raindrops is going off in another, the visible light at least, is going in a different direction, not towards you. And so, yeah, you're getting light from those raindrops in your direction, but it's not in the visible range. The visible light is going off in other directions, and so the sky will look quite dim, in fact, even dark between the two rainbows. So there's a lot of really cool optical phenomena. And under the cool physics, I posted several links that they've been up there for most of the semester, but I encourage you to go and look at them now because it's really quite timely. There's a lot of really cool optical phenomena, not just rainbows, but halos and glories. In that something else we see off of raindrops, it's kind of like the glass beads. We'll get a bright reflection right at 180 degrees. That's called halo scattering, that bright 180 degree reflection. And so one of my favorite things to do at Yellowstone is to go to a thermal feature with the sun directly behind me. So that if light passes right by my head, like really close to my eye, where it hits raindrops, I'll get a bright reflection back. And if you look at your shadow in the steam, you will see brightness around your head on either side of your eyeball, like right here and right here, from that 180 degree scattering, and that's called halo scattering. And the reason it's called a halo is because of the perception. It's very, very easy to think that what you're looking at is your reflection, but with a bright ring around your head, when really it's just bright spots on the other side of your head. It's easy for us to interpret, because we're pattern-seeking creatures, to think of there being a ring of light around our head. And there's actually some historical implications of this. In Western culture, mostly people seeking religious experiences on high mountaintops where they might look down and see their shadow in clouds. And if they have this religious experience, they've often associated that with the light around their head that they can sometimes see. And so there's often a spiritual element that's been ascribed to this halo scattering that we can see. But one of my favorite things to do at Yellowstone is, again, to look for this in your shadow when you look at steam coming off of a thermal feature. It's actually quite striking. So a lot of really cool optical phenomena you can see in the sky, especially this time of year, with the light reflecting and refracting off of ice crystals. You can see halos in the sky. You get the 22 halo off of ice crystals and the 40 degree halo off of ice crystals. You can get all sorts of arcs and patterns in the sky. And some of the links I provide on the website talk about the exact refraction that's going on with the ice crystals. They're hexagonal in cross section, forming either rods or plates. And depending on their orientation, you can see, and their presence in the sky, you can see different optical phenomena, like sundogs, arcs, and like the azimuthal arc, where again, it's a very low angle refraction. So kind of like what we saw over here with that triangle piece, you'll get a bit of a dispersion going on with the colors of light. And so it'll look like an upside down rainbow high in the sky, right above the sun. And that's from basically refraction off of ice crystals. Okay, so a lot of really cool optical phenomena you can see. So more practically, we can use this refraction idea to make lenses and to focus light. So here I have let's get these guys a bit closer. So let's turn off the lights a bit. So I have two rays of light going into this bent piece of plastic. And one side is flat, the side that's off to the left, the side off to the right is curved. And because of that, parallel rays will converge in what we call a focal point. Basically, this could make something very, very far away where the light is essentially coming in parallel, focus the light to a point so that if you're over here, something very, very far away might look like it's right here because this is where the light intersects and comes from. So a converging lens like this will create a real image of something very, very far away. And it doesn't matter which side is curved, whether or not the curving happens in the first face or the second face, it's irrelevant. Light will still be focused in the same place. And if we diverge the rays a little bit, so what I have is I've got two rays of light, and there's not much to look at, but if maybe if I just move it over a little bit. Yeah, that works better. This is like light coming from some point, right about over here where the door is. Imagine these two rays originating from someplace. So this would be our object over here by the door. And then the light would hit the lens, and you can see it's bent down, and it will make it look like it's here. So if you're over here, far off to the right, looking at something through this lens, something that's normally over by the door will instead look like it's right here, a lot closer to you. So you can magnify things and make them look like they're closer using these kinds of lenses. Contrast that to a diverging lens. Let's again try to make the beams parallel. This is a diverging lens where it's curved the other way. One way to tell a converging lens from a diverging lens is that a converging lens is thicker in the middle. A diverging lens, which spreads the light out, is going to be thinner in the middle. And so here we have light coming in close to parallel. So this would be like light coming from some very far away point where they intersect very far off to your left. But when they hit the lens, they spread out, they diverge. And so if you're over here off to the right looking at this, instead of having it look like the light's coming from someplace way over there, it's going to look like the light's coming from, right about where my fist is, on the other side of the lights. And so you can change where it looks like an image is. So this also creates something that might look like it's a bit closer. And let's go ahead and have the lights on. This is really useful for correcting eyesight. For example, if you're nearsighted, you can only focus on things that are really, really close. Basically, it turns out that if you're nearsighted, the lenses of your eyes and the shape of your cornea are such that where your eye and the cornea focus light is not on your retina. It's in front of your retina. And what's needed is to make your cornea and lens less converging. If the light could be spread out a little bit more, it would then be focused on the back of your eyeball. And that's why nearsighted people have diverging lenses that are thinner in the middle and thicker on the outside. Basically, so that the light, once it's divergent a little bit more, your lenses and your cornea are too converging, they're too strong. So putting a diverging lens in front of that focuses the light a bit farther away so it can be focused on your retina so you can see it. If you are farsighted, it's because your lens and cornea aren't focusing the light enough. The light would actually be focused at a point on the other side of your retina, behind your retina. And so you need to have more converging of that light in order for you to be able to see it. And so that's why people that are farsighted have converging lenses that are thicker in the middle and thinner on the outside. And for many people, you also have astigmatisms, which means that there's not a symmetry. It's not perfectly symmetrical. You'll have stuff to the right or the left or off at some angle, up or down, focusing on slightly different places. Basically, the plane at which the light is focused is not a plane, in parallel to your retina. It's off at some angle. So you might be more nearsighted off to one side and farsighted off to the other. Kind of bizarre. And So that's why the lenses in your glasses are often not quite symmetric. It's to adjust for a astigmatism. So basically, we could use curved surfaces to focus light. And the amount of bending in a surface, again, depends on the index of refraction. The more the light slows down, determines how much bending of the light you get. And some materials bend light a lot, and some materials bend it less. For example, glass bends light much more than water will. You get a much bigger change in angle if you're looking into glass or Pyrex or some plastics than you will, say, in water. And that the amount of bending you get on a surface depends on the difference on either side of that surface of the index of refraction. Basically, how much of a change in the speed of light you have at any one interface determines how much of an angle you get. If there's a huge difference in this index of refraction, in the speed of light, basically how optically dense two materials are, you'll get the light bending quite a bit. If there's not as much of a difference, you won't get as much bending. So let's do a slide. Let's do a PowerPoint question. Okay, so we have a parallel beam of light sent into an aquarium. If a converging glass lens is held in the water, where does it focus the beam? Closer to the lens than when the lens is outside the water, at the same position as when the lens is outside the water, or farther from the lens when outside the water. So the picture above shows where the light would normally want to focus. If the lens is in air, but if it's in water, will that light be focused closer, farther, or the same distance from that lens? Think about this for a bit, please. Okay, folks, that's enough time. Show me your cards. If you're online, go ahead and hit a letter on chat.
All A's so far, Dr. Steve.
Okay. Could I get a volunteer to defend why A would be correct? If you're remote, go ahead and unmute and just speak up.
Yeah, I'll give it a go. I chose A because I just figured the water would add more interference. I don't know if that's exactly the right word. That would make that convergence closer to the lens.
Okay, so water will make it diverge more. It basically adds to the amount of divergence you get from the lens.
Right.
And basically make the light focus even more. Okay? Can I get a volunteer to defend C that in fact would be farther away?
I chose C, like, I just guessed because I also went off what you said that that when light goes to glass, it bends more. I figured that it would have to be farther.
Okay, Ms. Merle? Yeah. Okay, so if I could summarize what Ms. Merle said, I don't know if that was very clear for folks remote, is that there's less of a difference between the refraction of the glass and the water, and it's a difference that's important. And so because there's a bigger difference between glass and air than there is between glass and water, we wouldn't get as much bending, and it should focus farther away. And nobody chose B, and that's just not going to happen. It's either going to be A or C. So I'd like to hear some discussion. Which of those explanations sounds makes a bit more sense? Or does anybody want to weigh in on any of the points raised? If you're remote, go ahead and unmute and say something. Folks in class, what do you think? I know we don't have a consensus in the classroom.
I still like the answer for A. Usually when I think of stuff in water, I think of like a fish in a river. It's kind of in a different position than when you think, or where you think it's at. So, thought that might be the same thing.
If it's in a different position, then it looks like that's because the light's diffracting more.
Anything showing up on chat?
There's a confusion about the defensive seat. There's confusion about the defensive seat, but nothing else.
Okay. Okay, well, if there's no more discussion, go ahead and show me your cards and hit that letter on chat. So what's it look like between A's and C's on the chat?
1C, the rest are A's.
Okay. Well, we have had an increase in the number of correct answers, which is C. Again, the amount of bending of light at any surface depends on the difference in the index of refraction at that interface. There is a large difference of the index of refraction between glass and air. Water does not refract light as much as glass does, but it sure as heck refracts light a whole lot more than air does. And since there's less of a difference in the speed of light and the index of refraction between glass and water, you're not going to get the light bending as much when light leaves glass and enters water, or leaves water and enters glass. And that means then if the light is bent less at that interface, right where the light leaves the glass and enters the water, you're going to get less bending, and that's going to make the focal point, or where the light is converging, farther away from the lens. For those of you who are nearsighted, you probably know from experience that your eyesight is improved when you're underwater. That's because you don't have as much bending of light between your the water and your cornea compared to what you would between air and your cornea. There's going to be a lot more bending. And the problem is with nearsightedness, well, the light is focused before your retina. And so the less bending that occurs, the better your eyesight is. And so that's why your eyesight is improved underwater if you're nearsighted, and it's worse underwater if you're farsighted. So there's kind of a practical application of this. But let's talk about where an object looks like. Let's go ahead and get to the next slide. This kind of gets to the point of an object looking like it's in a different place. And I know you've probably had the experience looking into water and thinking that the water isn't as deep as it really is. A classic example is you snag your fishing lure off on a log not too far from shore, and oh, that doesn't look very deep, I'll just wade out there and get it. Or, yeah, that creek doesn't look very deep, I'm just going to wade across it. I bet all of you have probably been in a similar situation, and you've been surprised that the water is actually deeper than it looks. Except I think I just blew the question.
I think you did.
I did. Okay, so here's the question. Does it appear to be nearer the surface than it really is, farther from the surface than it really is, or at the same distance that it really is? Really fast, just show me what you're thinking. Show me your card. What's it look like on A?
2.
Oh, sorry, on chat. Dang it. Is anybody choosing anything besides A?
Yeah, we got a mix of A's and B's.
Really? Okay, could I get a volunteer to defend B, please? Go ahead and unmute and speak up. Nobody in the classroom chose B. Anyone? Okay, well, I kind of blew this, so I think we'll just skip discussion. The correct answer is A. But let's draw a ray diagram. So we have, say, water surface. We've got, say a coin down here. We can draw light rays. Basically, every point on this coin is going to act like a source of light, reflected light. And if we have light, well, let's make the surface of the water a little bit closer. So we have air, water. We can imagine light going straight up from the coin. And when it hits this interface with the air straight on, there's not going to be any refraction. It only is when it hits at an angle. So the light will go straight up. Use your imagination. Think of that as a straight up line. Okay? And if light comes off at just a little bit of an angle, it's going to bend a little bit away. It's going to bend off in that direction. That's actually more bending than there really should be. That's a bit better. And then if it comes off at even a bigger angle, it'll bend at a bigger angle. And so if you're up here looking at the light coming out of the water from this point on the coin, it's not going to look like it's here. The light's going to look like it came from about here. So right here is where it looks like the light came from if you're outside the water. And that's going to be close to the surface. And you can do the same thing for a point over here. It's all going to look like the light came from a point right here. So the image of the coin will be about here. So here's the coin. And here is the image. Of the coin. And it looks like it's the same size. With a flat surface like that, it's not magnified at all. Because looking at it straight down at an angle, it looks like it's the same width that it is. And so here brings up the question, how come fishermen so often get the size of the fish that got away so much wrong? Because that's a common mistake, is to say, oh, the fish was this big. When really it was only probably about that big, which is still a pretty good sized fish. And that's because if you have an idea of how deep the fish is, by it appearing to be closer, you can be easily fooled to think that it's larger. So a flat surface like this does not magnify things, but it does make them appear closer. And if you're more cognizant of how far away it really should be, you can be fooled into thinking that it is bigger. But surfaces like this do not magnify things. They just change where they appear to be. Okay, so I'm going to put the projector on standby just so I don't have the light. And what I have here, is this ready to go with the?
Yep.
Yes, it is. Okay. So yeah, let's go ahead and dim the lights. Let's go ahead and turn those off. Okay. So what I have here is I have a light source. And let's just turn around so you can see the source. You see we've got the arrow going straight up. And we've got a little barbell that's off to the left. So the little circle is off to the left side of the source. And the arrow is pointing upwards. But if that light is sent through a converging lens, just like we saw on the screen, it will focus that light at a point, creating what we call a real image. So light is physically intersecting right here to make this image. And you can see that it's flipped upside down, and it's also mirrored right to left. Now, I don't know if this will show up very well if you're remote, but if I take away the screen here, let's see. Ms. Burrow, I think it's pointing right at you. If you look through the lens, it'll appear like this source is right where the screen was, because that's where the light came together and focused and converged right here, and then it's diverging from this point. So if you look through the lens, this right here where my fingers is where the screen was, is where it looks like that light source is. It looks a whole lot closer to you and quite a bit bigger. So this is magnifying something that's fairly far away, making it look closer and bigger. This is kind of like what telescopes do. And then Mr. Horsley,
Yeah,
you might be able to see it as well.
oh yeah, I can see part of it.
Okay, if you stand up, I bet you can see more of it. And Mr. Anderson, you'd have to stand way up. Yep, right a little bit lower, right about there. So it should look like its source is pretty close to you if you look right through the lens.
You're good.
Okay, does Braden, if you raise the camera, is that something that you can see in the?
I think it's blowing out. Yeah, that's not gonna work.
It's not going to work. Okay.
That white ball.
Okay. So. If I switch lenses, where's the diverging lens?
Between your notebook and your. I think it's right there.
Ah, it's already on the slide thing.
Yes.
Okay. Okay. With a diverging lens, we're not going to be able to create a real image. It's going to make the light look farther away. Well. And
Yeah, I can see it.
if you look through the lens, you could be able to see this, and you can see that it should be right side up. The arrow should be, yep, the arrow is going up, and a little circle ball should be off to your left. But it's definitely looking like it's farther away and smaller. Can you see that, Ms. Burrow?
Yeah.
Okay. And I can change the relative position by moving the diverging lens, but that's just about it. And we created a real image last time with this. If I move the lens a lot closer, now, is this even gonna? No, it's not gonna work. Because right here is, I can create a virtual image that should look really, really big. But it's going to be right side up now. So, Ms. Murrow, can you look through the lens?
Yeah,
Can you see the image?
kind of, yeah.
Okay, it should look bigger, but also, okay, that's too close. Right about here is probably where I can make it really, really big. So we're kind of magnifying it, but it's a virtual image. Light is actually not being focused. In fact, if you look at the spot of the light on the wall over there, it's basically a blur. But if you look through the lens, Mr. Horsley, can you see this? You might have to stand up.
It's definitely magnified, yeah.
And it's also right side up, before it was upside down.
Right.
So, using lenses in combination like this, go ahead and just turn the lights on. We can create images that are either very big or very small. And this is most useful to make small things big, or things that are very, very far away look closer. So with telescopes or microscopes. And so let's ask another question. Let's go ahead and do the slide thing. What happens if we block some of the lens? That's the next question. So, a converging lens is used to form a real image of an upright candle. Well, basically what we have right here on the screen, a real image. And if the upper half of the lens is covered by tape, what happens to the image? So if I cover part of the lens, the upper half, will it make the image disappear? Will it make it dimmer? Will the top half disappear? Will the bottom half disappear? Will the image just be shifted down? Will it be unchanged, or does it depend on where the observer is as you look at the screen? So I want you to think about this for a bit, because this is not a simple question and there's a lot of possibilities. But basically for the situation that you see right now, where we have the image formed on the screen. So Braden, do we need the camera for this?
You want to grab the.
So we're describing the situation I've set up right now on the optical bench, where you have this image. If I cover half of the lens, the upper half of the lens, and I'm just going to do it with this block of wood, what will happen to what you see on the screen here? That's the question. Okay, get your cards ready. Go ahead and show me what you're thinking. What does it look like on shot?
C's, B's, and D's, mostly C's.
Okay, but no A's?
Doesn't look like it.
Any F's or G's?
No.
Okay, so we have, just to be clear, B, C, D, and was there any E's?
No E's.
So just B, C, and D, that's it?
Yep.
Okay. So can I get a volunteer to defend B, that the image will just get dimmer?
I can try.
Please do.
So I just thought that the image would still reflect, even if it's covered, but it would just, there would be just less light going through, so it would be dimmer.
Okay, so the lens will still refract the light, and it's gonna refract light from pretty much every point on the image, and we'll just have less light, so it'll be dimmer. Can
Yes.
I get a volunteer to defend C, please? That the top half of the image will disappear if I cover the top half of the lens. A volunteer to defend that idea, at least, please.
I chose C. I just drew a picture, like kind of how you've been showing us all along with the converging lens. And I tried to draw the lines how they would appear for the image to be right side up. And then I cut off half of the rays. And that's why I chose C.
Okay, so drawing a ray diagram, it looks like the rays that are going to be blocked are the ones that would form the top half of the image, so that should disappear. Okay, can I get a volunteer to defend D, that in fact is the bottom half of the image that will disappear? A volunteer for D?
I could try.
Good.
So it's more of a guess, but just the way that the light is converging, I thought that it would also be flipping the image. I'm not sure if that's right, but with the image flipped, if you covered the top, it would actually be covering what appears as the bottom. So
Okay, so what we have here is the image we're getting, the real image is inverted. It is upside down compared to the source. That arrow is pointing down instead of up. And so because of that reversal, you're saying that by blocking the top half of the lens, we should block the bottom half of the image. Okay, those are all good points, and it's either B, C, or D. It's not A, E, F, or G. Those are not correct. It's either B, C, or D. But we're unfortunately out of time. This is where I'd like to start off then tomorrow morning, is with this discussion. And we'll actually demonstrate what's happened. Thank you for your attention, folks.